If higher altitude means less air resistance and better fuel efficiency, why don't planes simply fly at 60,000 or 100,000 feet? Engineers have chased that question since 1940, and the answer hides a phenomenon pilots call coffin corner. In 1940, the Boeing Stratoliner took passengers higher than ever before, thanks to the world's first pressurized cabin. Suddenly, airliners could soar above weather and turbulence, with a cabin atmosphere kept comfortable, even as the outside air thinned out. But every leap upward brought new risks. The de Havilland Comet, the first commercial jet, revealed a hidden danger. Repeated cycles of pressurization caused cracks to form in the metal skin, leading to deadly failures in the early 1950s. Engineers responded by redesigning windows, reinforcing fuselages, and setting strict fatigue limits, rules that still shape airliner design today. Then came the Concorde, built to cruise at 60,000 feet and twice the speed of sound. Its reinforced pressure vessel and thirsty engines allowed it to outclimb storms and traffic, but at a steep cost in fuel and maintenance. Even higher, the U-2 and SR-71 spy planes pushed past 70,000 feet, but only by accepting razor-thin safety margins and requiring pilots to wear full pressure suits. Each of these aircraft proved it is possible to fly higher, but the extreme solutions they needed, including special materials, unique engines, and life support systems, showed why the dream of routine, higher-altitude passenger flight never scaled up. The lessons learned from these pioneers set the boundaries for every modern airliner. At first glance, flying higher seems like a win for airliners. Less air means less drag, so should planes not just keep climbing? But as altitude rises, air density falls off a cliff. At sea level, air weighs in at about 1.225 kilograms per cubic meter. By 40,000 feet, it has shrunk to just 0.3, less than a third as thick. Here is where the physics gets interesting. To keep generating enough lift in this thin air, a plane must speed up dramatically. The lift equation, at its core, says that lift depends on air density, wing area, speed squared, and a factor called the lift coefficient. For a typical airliner and cruise, that lift coefficient hovers around 0.35 with a maximum near 1.6 in extreme situations. But density and speed are partners in this dance. If one drops, the other must rise. So at 40,000 feet, an aircraft needs to go about 1.8 times faster than it would at sea level, just to stay airborne. This sets up a new challenge. The faster you go, the closer you edge toward the limits of what the wings and engines can handle. Pilots rely on a speed gauge called indicated airspeed, or IAS, which measures how hard the air is pushing against the plane. But as altitude climbs and air thins, that number starts to hide the real story. At 35,000 feet, a jet might show 250 knots on the dial, yet it is actually slicing through the sky at closer to 450 knots true airspeed. This gap grows with altitude because the gauge is tuned for sea level air, not the thin air miles above the ground. To keep enough lift in thinner air, the plane must fly much faster than the instruments suggest. But there is a catch. Every jet has a maximum operating Mach number, usually between Mach 0.80 and Mach 0.85. Push too close to this limit and the risk of shock waves and loss of control rises fast. That is why pilots keep a close eye on both the indicated and true airspeeds, balancing the need for lift against the invisible wall set by the speed of sound. Jet engines depend on a steady gulp of oxygen-rich air to produce thrust. As an airliner climbs, the air thins out and each revolution of the engine's fan pulls in less mass. This means the engine can't make as much power even if the throttle is wide open. To protect against a dangerous surge where airflow inside the compressor goes haywire, modern engines use an engine pressure ratio cap. This limit keeps the compressor stable, but it also means less thrust at altitude. To stay aloft in thin air, the aircraft needs to go faster, but pushing for extra speed burns more fuel. Specific fuel consumption rises steeply as the engines struggle for oxygen. The drag may be lower up high, but the fuel penalty cancels out the gains, making higher cruising speeds expensive and unsustainable for commercial jets. Inside, Every airliner, the cabin feels steady and safe, but the shell holding that comfort is constantly under siege. At cruising altitude, the pressure difference between the inside and the thin air outside reaches about 8 pounds per square inch, enough to keep passengers breathing easily, but a heavy load for the fuselage. Each flight stretches and relaxes the metal skin, and over tens of thousands of cycles, even tiny cracks can grow. The de Havilland Comet disasters of the 1950s exposed just how dangerous repeated pressurization could be. Today, engineers build in strict fatigue limits and reinforce the structure, but every extra pound of strength adds weight and cost. The 8,000-foot cabin altitude standard is a compromise. High enough for safety, low enough to keep the structure manageable. Push higher and the pressure shell must grow thicker and heavier, eating into payload and efficiency. The higher you go, the more the structure itself becomes a barrier. At 40,000 feet, the speed window for safe flight narrows to a razor's edge. On one side, the stall speed creeps upward. If the plane slows even slightly, the wings cannot generate enough lift in the thin air, and the aircraft risks stalling. On the other side, the maximum safe speed drops because flying too fast brings the jet close to its Mach limit, where shock waves start to form and control becomes unpredictable. These two boundaries, one rising, one falling, squeeze together as altitude increases. For some jets, the difference between stall and Mach limits at high cruise can shrink to just a handful of knots. Pilots call this the coffin corner, a place where even small changes in speed or turbulence can push the aircraft outside its safe envelope. A Gulfstream business jet once found itself in trouble at the upper edge of its flight envelope. As the crew leveled off near 41,000 feet, the indicated airspeed dipped dangerously close to stall, while the Mach number nudged the maximum safe limit. Suddenly, the jet shuddered and pitched down. Lift vanished, and the plane began to fall. Only a rapid emergency descent brought the aircraft back under control. That narrow window between too slow and too fast is not just theory. It is a place where even experienced pilots can run out of options in seconds. Every safe flight relies on finding that sweet spot, high enough for efficiency, low enough for control. Today, altitude is not about chasing limits. It is about respecting them. Thanks for watching.